Today we're going to spill the beans on autosomal DNA transmission between generations. I imagine you have lots of questions and hopefully we'll be able to get some of them answered today. You've taken an ATDNA test and you have learned a fair amount about how DNA transmission works. You know that 50% of your DNA originates with each of your parents. Now, if that formula is true, then 25% comes from each of your grandparents, 12.5% from each great-grandparent, and so on. Sounds simple, but it's not quite that easy. You also know that you have 46 chromosomes, which are arranged in 23 pairs, with each pair being half from your father and the other half from your mother. And the 23 pairs of chromosomes are further broken down into two types. One is an XY chromosome, which is a sex-determining chromosome, and the remaining 22 are autosomal chromosomes, or ATDNA chromosomes, which determine pretty well everything else. I sense that you're puzzled and likely have some questions. I'm sure you want to know exactly how the process of transmitting DNA from one generation to the next actually works. And then I'm sure you're concerned with some of your matches. I'm sure you have some centimorgan matches with some cousins that are really high and then low with others, and you know of other cousins who have taken DNA tests, but you don't match them. So you want to know why. What's going on? Before we get into the demonstration, we need to talk about a couple basic assumptions. One is that if the pattern of inheriting half of the DNA from each parent is true, that means that 25% should come from each grandparent, and so on. Now, if that's the case going backward, that is up your family tree, it will also be the case going forward, down your family tree. So you will transmit 50% of your DNA to your child, and in turn, when they transmit DNA to your grandchild, it should be 25% of your DNA. So what goes up the tree goes down the tree. And the other thing that one needs to assume is that since we all have 44 chromosomes, half of which are inherited from our father and the other half from our mother, then each of those chromosomes make pairs. So you end up with 22 pairs, and that is consistent. You will always have 22 pairs, with one half of each pair being from the mother and the other half from the father. To answer your concerns, I put together a bit of a demonstration, but in place of chromosomes, I'm actually using beans, good old cooking beans. And for this purpose, I've chosen to use pinto beans, black beans, and white beans. The white beans are simply going to serve as a control mechanism or filler, represent the chromosomes being introduced by subsequent generations. So we've got the three types of beans, but you'll also note I've put yellow dots on about a handful of black beans and red dots on about the same number of pinto beans. I have not used any fancy helix graphics, nor colorful charts, nor graphs, just beans. And when it's all over, we're going to use the beans to make bean soup. So at the end of the day, you'll be able to say, Howes, you're full of beans. So now we want to look at the process of how DNA is transmitted between generations. You really want to know how that works. And to demonstrate that, I have placed 44 black beans, being 22 regular black beans and 22 dotted black beans in one can, and we've named that can black bean. And that's going to represent the name of the male donor, the father. And into the other can, I put 42 pinto beans, being 22 regular pinto beans and 22 red dotted pinto beans, and we're going to name that can Pinto Frijo, frijo being the Spanish word for beans. So now we've got the two donors, the two parents that are there. And so the next step is to create our offspring. And we're going to start with offspring A. So we have a separate empty can, another coffee can. And so you reach into black beans can and you randomly select 22 beans and put them in the empty can. Then you reach into Frio's or Pinto's can and you select 22 beans there. So now we've got a total of 44 beans in this offspring A can. And so the next thing you really need to do is examine them. And so you'll see that offspring A has 13 black beans, 9 spotted black beans, but also has 12 pinto beans and 10 dotted pinto beans. So in either case, it's 22 of each. So we have offspring A. So the next step is to create additional offspring, offspring B, offspring C. And to ensure consistency and accuracy, we need to go back and replenish both of black beans and pinto beans cans with the exact amount of beans and ratio of beans that we initially started with. In other words, 22 black and 22 dotted, and in the other one, 22 pinto and 22 dotted. So once that's done, you repeat the process for B and for C. Now, if you have that completed, you'll note that offspring B has 12 black beans and 10 dotted black beans, and then 11 pinto beans and 11 dotted pinto beans. And just like the other, it tallies up. You have 22 black beans and 22 pinto beans. And when we look at C, you'll see that it's 12, 10, 9, and 13. And the same thing happens there. You'll have 22 black and 22 pinto beans, but all the ratios are different. So the next step, because this is only 3, we want to look at numbers, don't we? So we're going to repeat this whole process 7 more times. So we're going to end up with kids D through J, and that we'll look at on the next page. So now that you've completed testing for offspring A, B, and C, and you've looked at the graphs or the pictures that we have for them, it was time to do D through J. And rather than doing pictures, we thought we'd just simply put all the data on a chart where we can examine it, look at tallies and averages and the likes of that. And so this is what we've come up with here. If you look at D, you've got 7 black, 15 dotted black, 11 pinto, and 11 dotted pinto. And then down the list, you'll see that everything varies considerably. You've got the highest being of 15 dotted black beans, but also at one point you've got 15 dotted pinto beans. So it's a wide variation, but it's the totals that we're after. Now, I've just used 10 examples here. If you were going to do it the right way, you should probably use a minimum of 100 or 1,000 tests. But this would give us a good idea of how things work. So if we look at our totals and our averages, for the black, we've got 24%. For the dotted black, we've got 26%. For the pintos, we've got 23, and for the dotted pintos, we've got 27. So if we look at that, we've got a percentage range of 23 to 27%. So I guess to say that 25% plus or minus falls within that, so that's pretty much right. But you can also look at medians, and if you were to lay all these numbers out, starting with the lowest, going to the highest, and then looking at the middle, the median, you'll see that it is 11. And that works out to be 25%. And that happened 30% of the time. And if you look at the median range, which goes from 10 to 12, that happened 20 out of 40 times, or 50% of the time. So 50% of the time, it's exactly 25%. So an average of 25% plus or minus is good. Now, you might want to use the word about 25% or approximately 25%. Either way, it's not cut and dried and can fluctuate a little bit each way. So then if we were to look at the great-grandchildren, and we have been told that it looks like they're going to be at about a 12.5%. And it means another test, but based on how random selection seems to be, it's probable that that will be in the range as well. So 12.5% plus or minus, that's probably good. So, but the thing that this does not take into account, it does not take into account any natural DNA selection that may be as a result of some predetermined condition. It's strictly chance or random selection. And that's what's most prevalent in the overall process. So that takes us to the next part of our demonstration. We want to find out why you have high centimorgan counts with some cousins, low with others, and yet with even others, you don't have matches at all, and yet they've taken the test and you know for sure they're your cousins. So you want to know why. Once again, random selection is the likely reason, and to demonstrate this, I began with the same offspring examples, A, B, and C, that I had used earlier. But this time, instead, I tracked their descendants down through successive generations. So you can see the three offsprings right below, A, B, and C. So let's see what happens. Although the process may seem quite complex and involved, it really is straightforward. It essentially involves repeating the procedure 4 times over the 4 different generations that we want to deal with. We're going to start with the grandchild generation, which we will label A1. And to achieve this, I placed offspring A's 44 beans into a container. Then I randomly selected 22 of those beans and put them in another container, to which I added 22 white beans. The white beans are representing A1's other parent. Now that gives you a total of 44 beans in this last container. And in there, we want to know the number of black beans, the number of dotted black beans, the number of pinto beans, and the number of dotted pinto beans. The white beans, they're there. We know we got 22 in there, but we really don't need to know anything about them. Then to move on to the great-grandchild generation, which we're going to call A2, I placed all of offspring's 1's 44 beans into another container, and then randomly selected 22 of those beans, put them in yet another container, and then I added 22 white beans, representing A2's other parent. Now there's a total of 44 beans in there. Like we did before, we tally up the number of black beans, the number of pinto beans, the number of dotted black beans, and the number of dotted pinto beans. And we completely ignored all the white beans. They're insignificant. Then we moved on to the next generation to achieve the second great-grandchild generation, which we're going to call A3. I placed all of A2's 44 beans into a container, then randomly selected 22 beans, to which I added 22 white beans representing A3's other parent. Now this was done in yet another container. So now there are a total of 44 beans. Again, we tally the number of black beans, the number of dotted black beans, the number of pinto beans, and the number of dotted pinto beans. Like we did the last time, we ignored all the white beans. And finally, to achieve the third great-grandchild generation, which we're labeling A4, I placed all of offspring A3's 44 beans into a container, and then randomly selected 22 beans, put them in yet another coffee can, and then I added another 22 white beans representing A4's other parent. Again, our total is 44 beans. And finally, we tabulate the number of black beans, pinto beans, dotted black beans, and dotted pinto beans in that container, and likewise ignored the white beans. The process was repeated again twice more, once for offspring B and again for offspring C, and that is explained in the following slide. So now that we have the procedure out of the way for offspring A, B, and C, we're going to take a look at what we found. I didn't mention that I took photos of each of the groupings of beans, and I labeled them accordingly, and then I grouped them in the photo that you see here, or the graph-like, so that you've got the first cousins being A1, B1, and C1 across from one another, and similarly for the second and third and fourth cousins. So now let's take a look at what we found. If we look at the first cousins, you're going to see a vast difference in the grouping of the beans, or chromosomes if you want to refer to them as that. So A1 has 4 black bean chromosomes and 7 spotted black bean chromosomes for a total of 11. B1 has 7 and 4, and C1 has 5 and 5. So you see that everybody's different here. And if you look at the pinto beans, you're going to see even a bigger difference. You're going to see that A1 has 4 regular pinto beans and 7 dotted pinto beans. B1 has 6 and 5, and C1 has 4 and 8. So there's a significant difference. So when you're looking at matching, this is going to show up. That's going to be why you have stronger matches with one cousin and maybe a little weaker with others. Now, these are first cousins, and your first cousins are all going to show relatively high centimorgan counts if you're looking at the results that you have in either Ancestry, MyHeritage, or any of the others. Now, when we drop down to the second cousins, you see a dramatic reduction in the number of beans. You'll see that the matches likewise dissipate. So A2, which is the second cousin, they have 3 black beans and 4 spotted black beans for a total of 7. Then they have 2 pinto beans and 3 dotted pinto beans for a total of 5. So now you got 7 and you got 5. If you look at B2 in comparison, you've got 4 black beans and 3 spotted black beans. It's pretty much the reverse ratio as to A2. And then if you look at the pinto beans, it's a further reduction. You have 2, just like A2, but you only have 1 spotted pinto bean. And that's significant. There's a big reduction here. So there's quite a difference between A2, the spotted pinto bean, and B2, the spotted pinto bean. Then if you go over and you look at C2, everything is different here again. You have 2 black beans, 2 spotted black beans for a total of 4, and then you have just 2 spotted pinto beans. The significance in this one is that the regular pinto bean is gone. It's completely eliminated. It's no longer there. And the others are significantly reduced. So then if we look at the third cousins, you see the same thing happening again. Everything is depleting, dwindling, or fizzling. And so cousin A3 has 2 black beans and versus cousin B, who has 3, versus cousin C, who has 1. So you got quite a difference there. And then if you look at the spotted black beans, it's 2, 1, and 1. And if you look at the pinto beans, gee, nobody has a regular pinto bean. You've got cousin A3 with 2, B1 with 1, and C3 with 1. Then finally, if you go down to cousin 4, you see the change again. It's this scaling down, it's this reduction, and it's all because of random selection. Now, the thing that I do want to point out here is that we are talking about the grandchildren or the descendants of black bean and pinto frio. And so they come down in pairs. So you've got the black beans and the spotted black beans as being black bean. And you've got the spotted pinto beans and the regular pinto beans as being pinto bean. And the significance of these spots is that the black spot represents, say, the father of pinto bean, whereas the yellow spot represents his mother. And the same is true for pinto bean. The plain pinto bean represents her father, and the spotted pinto bean represents her mother. So what we have in the very end, we do have their third great grandchildren, but we go more. We actually show the fourth great grandchildren of their parents. So you can see what happens here. In the fourth cousin level, the black bean surname or the black bean gene is completely gone. It's no longer there, completely removed from the equation. And at the same time, the pinto bean, it's completely gone. There's no DNA there from those two ancestors. That's A4. And if we look at B4, well, they have one of each of the black beans. So both black beans' parents are represented. So they both filtered down through that many generations. And when we look at the pinto bean, it's gone, and it's just pinto bean's mother who survived. And then if we look at C4, we'll see that it's similar to A4 in that both the black bean and the pinto bean chromosomes are completely gone. So it's the filtering down process through random selection which causes this phenomenon where your ancestors, their DNA, will completely disappear over time. So what do you get out of this? What's your takeaway? One not only receives 50% of one's AT DNA from each parent, but we know that each person transmits 50% of their AT DNA along to each of their offspring. We also know that AT DNA transmission is not equitable coming from the parent. Although each sibling receives 50% from each parent, it is not the same 50% mix received by the other siblings. Second cousins and closer kin will always share DNA, but the amount of DNA shared will diminish in generations further away from the donor parents. Despite a defined 50% AT DNA transmission pattern, random selection plays a major role right from the very beginning and results in some AT DNA diminishing or fizzling out in the long run. Random selection is the sole reason for high AT DNA matches with some cousins, low with others, and yet no matches with other cousins with whom you know you are related. Thanks for viewing this slideshow. Although the demonstration is somewhat oversimplified and not scientific, it does show the significant role that random selection plays throughout the entire autosomal DNA inheritance process. Thanks again.